Let's roll sound.
Rolling.
And action.
All right, BC students, welcome to 10-2, and we continue to do more exciting things that I just love to teach. Chapters 10, 11, and 12 are so cool. So 10-1, I'll go ahead and tell you, that was L'Hopital's rule. We also do that in AB class, so that's not a BC exclusive. Pretty much 10-2 for the rest of the year is all just solid BC, all right? So we are in the thick of it now. Okay, so we're going to start off with one of our old favorite segments.
And now it's time for Indeterminate Conversations with Mr. Wade.
And on that note, we debut indeterminate form number 4 today. 4, 5, 6, and 7 only seen in BC calculus. So we've got 0 times 20. Okay, we all know that 0 times 20 is 0. Determinant. Then we have infinity times 20. Well, infinity times anything just wants to blow up gigantic, right? 20 infinities is still infinity, okay? Obviously. So when you multiply by 0, it wants to make everybody 0. When you multiply by infinity, it wants to make everybody infinity. Start thinking about that, right?
What about infinity times infinity?
Well, infinity times infinity is even larger, so it's still infinity, of course. Okay, and then you get to the last one. 0 times infinity. 0 wants to multiply and make you 0. Infinity wants to multiply and make you infinity. Clash of ideas. Indeterminate. 0 times infinity can equal 1/5. I mean, you never know. So let's put NEI for not enough information. But then we'll also note that this is indeterminate form number 4. Or at least what I refer to as number 4. I've kind of ranked these from most common to least common. All right. And so this is the one I call number 4. Just outside those other 3 we talked about in that previous chapter, chapter 8. Okay. So now that we know this, let's check out the first example. So how would a BC or Calc 2 student deal with a limit like this? Well, here's the first thing we need to note, since we've kind of barely talked about this. In the first semester, when you take a derivative of a function times another function, you have to do the whole product rule, right? Ho-de hi plus hi-de ho. You can't just take the derivative, and then sandwich them together, right? Not with multiplication, not with division. Only if it's addition subtraction in there can you do a separate derivative, right? When you integrate, you cannot integrate 2 functions and then just multiply them together. That doesn't work. Addition, subtraction, yes, not multiplication, division. So let me just be very clear that in limit world, limits are very different. You can take the limit of the first one, take the limit of the second one, and sandwich the 2 answers together. Believe it or not, it's pretty amazing that you can do this with limits. So everything is fair game with limits. No product rule, no quotient rule, no integration by parts. When you had like the 2 things multiplied together, you had to do the late method. Remember all that? Okay, not necessary. So do each limit, okay? Everything works with limits basically. Like literally you can do whatever you want. So we're going to do the limit as x approaches 0 from the plus side, the right side, of x to the 10th, and then we'll separately do the limit as x approaches 0 from the right side of natural log of x. We'll multiply our results together. Okay, well, x to the 10th is x to the even. X to the even is nothing more than just a tall, skinny, parabola-like figure, right? Way steeper than x squared. Okay, isn't this a case where when you approach from the right side, it's continuous, and you just get a closed circle? So that's an easy limit. Yes, you can just take 0 and plug it straight in for x, which is how you always start a limit anyway. 0 to the 10th is 0. Okay, so clearly, if we just had x to the 10th, the answer would be 0. Now let's do the limit as x approaches 0 from the right-hand side on natural log of x. Step 1, you just try to plug it in, right? Well, you can't because you can't take the natural log of 0. Step 2, can you draw a graph and just look at it graphically, right? And then kind of, I guess, step 3 is like conceptually, can you figure it out, okay? So what I would do is just draw the natural log graph here. We know what it looks like. We've drawn it 10,000 times. As you approach 0, which is the y-axis, from the right-hand side, this curve, the closer it gets to x equals 0, the more the y is being pushed downward. And the y is approaching negative infinity, if you notice that there. Okay? So this limit is 0, that limit is negative infinity. So our answer is going to be whatever 0 times negative infinity is. You could move the negative out to the front if you wanted to, by the way. It's really just negative and then 0 times infinity. 0 times infinity is our newfound indeterminate form number 4. And 0 times negative infinity is just as indeterminate. That does not help. Okay, so what do we do when we get an indeterminate form? All right, we just learned that there is something called L'Hopital's rule, discovered by Bernoulli, of course, where you could get out of the indeterminate form. Problem. Anybody remember our little discussion last time? That L'Hopital's rule only works for 0 over 0 and infinity over infinity. Only those two forms work with L'Hopital. I'm going to put an L apostrophe H. Not in honor of the fraudulent mathematician, but in honor of the name of the rule. Okay, we'll do that. So here's the thing. If you can get it to be one of these two forms, L'Hopital's is on. L'Hopital's does not apply to 0 times negative infinity, but I wonder if we could finagle very cleverly with our math skills this equation into one of these L'Hopitalable forms. Yes, we could. This might be a good time to draw a bar down the page, because I'm actually going to end up doing 3 different columns here with you, and I don't want you to write too far over to the edge here. Try to stay a little bit contained. Don't write too big, okay? We've got a lot more writing to go, or go to a blank sheet of paper. All right, so now, column 2. Let's see if we can rewrite this function in a different way. So let me start with the limit as x approaches 0 from the right-hand side. We know we have that, okay? You'll notice that the two L'Hopitalable forms, they are fractions. They are division, and that's multiplication. I kind of need to tweak this into some sort of division problem, all right? So what about this for a clever idea? Once you see a math teacher do it once, you're like, wow, I'll never forget that, and I think I can do it in the future. You could move x to the 10th to the bottom, but wait, that wouldn't make mathematical sense, right? But what if we called it 1 over x to the 10th, the reciprocal of x to the 10th over 1? It's kind of like keep, change, flip, but you're doing it in reverse. Okay, you're flipping it to the bottom and going back to division. Or could you take natural log of x, move it under the x to the 10th, and call it 1 over natural log of x? It's reciprocal. Mathematically, these are true. Both of these are true. Well, I'm going to leave the natural log. Why? Because I've done this problem 10,000 times, and then I'm going to give you a little gem to tell you what I did. I'm going to move the x to the 10th instead, and I'm going to move it to the bottom. I'm going to call it 1 over x to the 10th. Now, I want to show you what that did for us right there. It's pretty amazing. If you apply the limit, and again, with division, only in limit world, you could do each limit and then just divide the results. You can actually get away with that, right? Not with derivatives and integration. If you take the limit of natural log, we already did that, right? That's still negative infinity. That's unchanged. So the top is negative infinity. But what about the bottom, all right? 1 over x to the even, we've been talking about these recently. 1 over x to the even is a hyperbola, but it's a volcano because it's x to the even. If you remember test number 9, okay? Cross of asymptotes, the little volcano hyperbola. As you approach 0 from the right-hand side on the 1 over x to the 10th graph, the closer x gets to 0, the more the y's are going to infinity. Oh my goodness gracious. Do you see what we just got? Negative infinity over infinity is a L'Hopitalable form. The negative does not mess it up. It's this form right here. That means L'Hopital's rule is on. So it's just a little bit of a reciprocal to pull it off. And isn't that so clever, right? So very clever. Now, just a little side note in this second column. We are going to have a third column, by the way, so save room over there. But in the second column, just a little note. This is going to take another 4 steps and we will be finished. All right? Sure, you know, back in middle school, you would have said 4 more steps. You know, in BC calculus, we're like, oh, good, only 4 steps? That's a break from some of the 25-step, you know, like the trig substitution. Oh my gosh, that thing can go like 25, 30 steps in worst case scenario. So 4 more steps, we're done. Let me just show you a little something. What if you had decided to move the natural log of x instead? So the x to the 10th would have stayed upstairs. And then natural log of x would have flipped and it would become 1 over natural log of x on the bottom. Okay, that's also valid. These are all the same thing. They're all equivalent, right? If you do this one with L'Hopital's rule, you can do infinite L'Hopital rules and you never escape the indeterminate form. Can you believe that? Infinite loop that you cannot escape. Meanwhile, the other one's going to be 4 steps. Talk about a colossal misstep, right? You just went from, I can solve this pretty soon, down to, well, I'm going to be off by infinite steps, right? Okay, yeah, not good, all right? Inescapable. So that's why you don't want to do that, and I'll give you a gem, of course, in a second. Okay, now we can go to a third column. We'll need to erase this stuff over here, of course. All right, so how about this for a new trick? Hey, it actually worked. I hope it did. Okay, third column. Since we have negative infinity over infinity, we can now apply L'Hopital's rule to this one. We're not going to do that one, right? To this one. So if it's in the indeterminate form of infinity over infinity, you can do limit as x approaches 0 from the right-hand side. You can take the derivative of the numerator, derivative of the denominator, retry the limit, see if it works. The derivative of natural log of x is 1 over x times chain rule of x is 1. The derivative of 1 over x to the 10th, i.e. 10x to the, x to the negative 10th would be negative 10 comes down, x, derivative means drop the power by 1, to the negative 11th, okay? Let's clean this up a little bit. We'll do some algebra to make it look better and see if we've escaped the indeterminate form. And if we haven't, we'll do another L'Hopital's. So now we'll do limit as x approaches 0 from the right-hand side of 1 over x divided by, let's call this negative 10 over x to the 11th, right? Because you don't want to leave x to the negative power. So wouldn't you put it under the negative 10? Fraction divided by a fraction. Keep, change, flip. We're going to flip it back now. So we're going to flip and multiply x to the 11th over negative 10. I like where this is headed because I see x's canceling out. I see us getting back to a nice normal function. This is amazing. Limit as x approaches 0 from the right-hand side. One pair of x's is going to cancel. So you'll end up with x to the 10th on the top after the cross cancel times 1. On the bottom, you only have negative 10. Of course, we like to put our negatives on top. Not that it's a big sin to leave it on the 10 right now. Now, retry the limit. We are not indeterminate anymore because the bottom is 10. That's not 0 over 0, and it's not infinity over infinity. Take the 0, just plug it straight in for the x. 0 to the 10th is 0, and 0 divided by 10 is 0. Final answer, 0. How about that? Okay, circle it, donut, sprinkles. All right, so final answer. Now, wait a minute. Where did we start this? We said it was 0 times negative infinity, right? Sometimes 0 wins. Sometimes infinity wins. Sometimes 0 times infinity is 7. You never know. Okay? Final answer is 0. That is the only way to do that limit right there. So today is kind of about modifying these limits, some of the funkier limits, to make them into L'Hopital's. Okay, a gem associated with what we just did. All right. Do not move a natural log of x, or I guess for that matter, a log of x. So we'll put like the regular log log. You'll occasionally see the log in calculus, but usually natural log, much more common. So do not move those in your attempt to get, let's say, to get 0 over 0 or infinity over infinity. Because you know what that leads to? What did we say? That leads to the infinite loop of disaster that you can never escape, right? An inescapable loop of L'Hopital where you just keep getting indeterminate, okay? There is an unless, okay? Unless, rarely, you'll see them both be logs. Okay, you'll have like 2 different logs multiplied or divided together. Well, they'd have to be multiplied because division would be okay. So if you see 2 logs multiplied together, then you're going to have to move one or the other, and you kind of choose the lesser of 2 evils, okay? So remember that. All right, so that's why I didn't move the log, because you never move the log. All right, we're coming up to a mnemonic device later, by the way, too. Now, do you recognize from pre-calculus the old sine graph, right? Right through the origin, right? It's called an odd function because it has origin symmetry. So y equals sine of x. Now, you will have to know a little bit about the cosecant graph. Now, that's one of the lesser important things, I think, in pre-calculus after teaching it for 20 years myself, all right? How the heck do you graph the cosecant of x? Well, this might be the only chapter of calculus where you really need to know what the cosecant graph looks like. Although all pre-calculus students do it. So, low on the importance scale, hey, what if you're sitting there in college and you can't remember how to graph that stinking cosecant of x? Well, cosecant, it is the reciprocal of sine. You do need to know that, of course. All right, that's a fact. So now let's think about this, okay? Where does sine of x equal 0? Well, the sine of 0 is 0. The sine of pi is 0. The sine of negative pi is 0, right? The sine of 2 pi, 3 pi, 4 pi, all the whole pi's gives you 0, doesn't it? Okay? But cosecant is 1 over sine. So every time sine equals 0, wouldn't that put a 0 on the bottom of your cosecant value? And 1 over 0 is undefined, right? Not indeterminate, undefined. So every time sine is 0, cosecant is undefined. What happens on the cosecant graph? What kind of undefined is it, Mr. Wade? Is it a hole? Is it a vertical asymptote? It's a vertical asymptote. Sine is 0 at pi, so cosecant becomes undefined. The sine of negative pi is 0, so cosecant becomes undefined because that 0 is down there in the bottom, right? So the easy way to remember the cosecant graph is that every 0 on the sine graph turns into a vertical asymptote on the cosecant graph. And at every peak and valley, the cosecant and the sine actually have the exact same outcome because aren't peaks 1, right? Peaks are 1, and 1 over 1 is 1. See, it doesn't change, does it? So the peaks and valleys are the same, but then cosecant, instead of going down, it actually bends up into the asymptote, up into the asymptote. You can never touch a vertical asymptote. And then this one bends down and down, okay? And cannot touch the vertical asymptote. So in a pinch, if you forget the cosecant graph, you can always think about sine. You can just put the little U shape on top of the peak, an upside down U on the valley, put a bunch of asymptotes in there. And so the black marks are actually the cosecant graph and the red is still the sine graph, okay? And cosecant is just an infinite bunch of U's that just go up, down, up, down, up, down, up, down. All right? So we'll need that little bit of knowledge from pre-calculus to proceed. And now let's try the next problem. So BC limit, Calc 2 level limit. Take the limit as x approaches 0 from the right-hand side of the very interesting function x times cosecant of x. Okay, you can graph cosecant. I would not suggest graphing x cosecant of x. Very strange graph. All right, so I can't graph it. I could try to take the limit, though. I could try to plug in 0. So if this is multiplication of x times cosecant of x, of course, only in limit world could you actually take the limit of the first function, take the limit of the second function, apply the limit as 0 as you approach 0 from the right-hand side to both of those, and then just multiply the results together. Only in limit world could you get away with just separate limits, right? Okay, as we mentioned. Now this is just a line. Y equals x, right? Y equals x is just the classic 45-degree diagonal line. Just take 0 and plug it into x and you get 0, right? That's an easy plug-in limit. Okay. Cosecant graph. All right, this would be the one time you'd have to know it. As you approach 0, i.e. the y-axis from the right-hand side, the cosecant graph gets forced upward, and the closer you get to that vertical asymptote on the y-axis, aren't the y-coordinates going to infinity, right? So this one's infinity. Now, if that had been a negative and you approached from the left-hand side, that little U shape would be forced down to negative infinity. Notice the difference in their directions, okay? That can have an influence. So you just kind of want to have a rough idea of the cosecant graph. Usually you'll be approaching 0. They're never going to approach something weird like, 7 pi over 2, or that would be too easy anyway. 8 pi, they're not going to do that, okay? They're probably going to pick 0. Now, 0 times infinity is indeterminate form number 4, as we're studying today. We're doing all the 0 times infinity cases today. So 0 times infinity is n determinate, we'll put IND for indeterminate. So you can't determine the answer yet. It's not even in a L'Hopitalable form because it has to be 0 over 0 or infinity over infinity. Second column, draw a bar. Get that thing to be in a better form to create 0 over 0 or infinity over infinity. All right. Now, it's your choice. You could either move the x to the bottom underneath the cosecant and call it 1 over x, the reciprocal, or you could move the cosecant of x under the x and call it 1 over cosecant, although wouldn't that just be sine, right? The reciprocal of cosecant is sine. Okay, your choice, but of course, listen to Mr. Wade, because I've done every single one of these like 10,000 times, right? And I happen to know that it's a little easier to move the trigonometric function. So I'm going to keep the x right where it is. I'm going to move the cosecant underneath and flip it and call it sine of x. So those are identical functions right there, okay? Just looks a little bit better over here. Let's see if we got our 0 over 0 or we got our infinity over infinity. Now, first of all, when you plug in 0 for x, that is 0. Plug in 0 for sine of 0 is 0. So this is just straight up 0 over 0, like no tricks. Just plug in 0 and it's clearly 0 over 0. Great, we're in a L'Hopital form, okay? And by the way, I'll go ahead and tell you, this is going to take 3 more steps, which we'll do in the third column here in a second, all right? Anybody curious? Maybe you are. Mr. Wade, what would have happened if I had actually moved the x underneath? Actually, not too catastrophic this time, not some kind of crazy infinite loop, but let me just point this out. The limit as x approaches 0 from the right-hand side of, if you had kept cosecant on top, and you had moved the x to the bottom but called it 1 over x. Okay, mathematically correct, all right? By the way, this version gives you infinity over infinity. So it still gives you a L'Hopitalable form. So see, that's still good, okay? So this is infinity over infinity. You can look at the graph and also look at the hyperbola graph and figure that out. But the point is, it's okay. It's just, it's going to take another 3 steps plus a horrendous amount of simplifying, okay? So let's say 3 steps of just the L'Hopital's rule, just that part right there, plus more, let's say, okay? So I would rather do 3 steps than 3 steps plus a bunch of cumbersome mathematics and algebra, right? So I'm going to give you some more gems, don't worry. I'm going to tell you what to move at what time. How do I know? By just doing all of them in my lifetime. It's the only way I can figure out the patterns, all right? And I don't hear about any teachers teaching the patterns. That's why this is going to be a gem for you because it's not published. All right, so not bad, not really that bad, better, okay? Now, let's make some space over here. Let's do the rest of this. Column 3. And I hope you love this stuff as much as I do because it's so clever. So we established that this was 0 over 0 already, right? That means L'Hopital applies. So limit as x approaches 0 from the right-hand side. The derivative of x is 1. The derivative of sine of x is cosine of x times the chain rule of x, which is just a times 1, of course. Guess what? We escaped the indeterminate form. That's not 0. That's not infinity. There's no way this could be indeterminate. Take 0, plug it in for cosine, and you get 1 over cosine of 0. Plus side not even necessary because cosine exists at 0, right? Now, if cosine did not exist at 0, then you have to start worrying about the right-hand side and like, where things are being pushed, But not in this case. If you can just plug it in, you kind of ignore the plus or minus sign if you notice when the function's continuous, okay? I'm not counting a step as where I just rewrote it because rewriting, that's not really a step. Step 1 was to do a very, very easy L'Hopital's. Step 2 was to simply plug the 0 in, and then the cosine of 0 is a peak, which is 1. 1 divided by 1 equals 1. Final answer. That was step 3. Did you see how easy those 3 steps were? Okay. That other version would have taken a triple L'Hopital's and then taken a whole lot more work, and we don't want to do that. All right? We want to do the much easier way. So final limit is 1. Just that easy.
On and on and on. I said, and it's on and on and on.
So that brings to mind another gem. All right, so what did Mr. Wade discover doing all these limits every which way possible? Well, I figured out that, remember, you never move logs unless they're both logs and you would have to, right? So pretty much never move logs. Guess what? Always move the thing we just saw. What was it? Cosecant and tangent and secant and cotangent. All four of those, okay? This is an always situation. Like if you don't move those, you cause so much work for yourself and you usually get stuck and you can't make it out. Or you might even hit a derivative we've never talked about before. And you're like, how do I even take the derivative of that? You're probably in the wrong place. So always move, I've discovered, tangent of x, and then the three reciprocal trig functions. What are they? Cosecant, that was the one we just saw, secant of x, and cotangent of x. Okay? So move those four trig functions immediately. Now you might be thinking, of course, a good calculus student would be thinking, what about sine and cosine? Sometimes they move, not often. So let's say sine of x, cosine of x, sometimes, okay? But not nearly the priority of tangent, cosecant, secant, and cotangent, all right? Those four have got to move, okay? So kind of keep that in mind as we do some more of these. All right, let's try the next one. Now we might need a really quick trig review here as well. So the tangent graph, I mean, of course, we've done the tangent graph a lot, so I'm sure you probably remember this. It's just a bunch of snakes, and then you've got those asymptotes at all the half pi's, right? So like negative pi over 2, positive pi over 2, tangent of 0 is 0, and then what happens? You get another snake, right? And then you get another crossing at all the whole pi's, or the integer pi's actually, right? So pi, 2 pi, 3 pi, those are all zeros. Negative pi is a 0, negative 2 pi is a 0. Every single half pi, like 3 pi over 2, is a vertical asymptote. So you'd want to know the tangent graph. Okay, we'll label that tangent of x. Okay, but that one we do fairly often. Sine, cosine, like every week it feels like. So tangent, important. Now, one of those rare graphs that you do them in pre-calculus, you hardly ever see them again. In this chapter, you have to know a little bit about them, okay, just to kind of get your bearings. And that is the cotangent graph. All right. So the cotangent is the inverse of tangent. And when we say inverse, we mean opposite world, right? So everywhere the tangent is a 0, well, the cotangent graph is a vertical asymptote. So now there's a vertical asymptote at 0. And now when you get to pi, there's a vertical asymptote on the cotangent graph, all right? And then at negative pi, down here, there's a vertical asymptote. 2 pi, 3 pi, 4 pi, all these infinite asymptotes raining down. What happens to all the asymptotes, like pi over 2? Those become zeros, x-intercepts, roots, right? And then 3 pi over 2 converts from a vertical asymptote to a 0. So if you ever forget, and I forgive you for forgetting the cotangent graph, I do not forgive you for forgetting the tangent graph, because tangent, we do that too often, all right? Sine, cosine, no forgiveness. But if you ever forget the cotangent graph, I will forgive you because we use it so rarely, and even in college. But just draw a tangent, do the opposite, and then this really is the opposite or inverse. Even the snakes are backwards. The cotangent snakes go in reverse, kind of like this. Okay, another asymptote right there. And it's an infinite bunch of backward snakes. And all of the intercepts have become vertical asymptotes, and all the vertical asymptotes have become x-intercepts. Okay? So kind of simple to remember in a pinch. When you forget, you can always find a way to remember. All right? So now let's go to our first column over here. So what do we do first? Okay, let's break this into pieces. Does the divide by 3 really matter? Not at all. Not really, right? That's not really part of the action. Couldn't you just do the limit of the top and then just divide the answer by 3? Sure, absolutely. So let's do the limit as x approaches pi over 2 from the right-hand side of the tangent of x first. Let's figure out what that is. Okay, we know our tangent graph. When you approach pi over 2, the vertical asymptote from the right-hand road beyond it, the closer I get to x equals pi over 2, the more the tangent graph dives to negative infinity for the y-coordinate, right? Okay, so there's my first assessment. Then I try the other one. Limit as x approaches pi over 2 from the right-hand side of 2x minus pi. Okay, you take pi over 2, you can just plug it straight in. Pi over 2 times 2 cross cancels the 2's. You get pi minus pi, which is 0. Easy one right there, right? That one's more, do I know the graph? This one's just a plug-in. And then you realize it's negative infinity times 0 over 3. All right. Negative infinity times 0. Don't even worry about the over 3. This is indeterminate form number 4. This is our focus today. What happens when you get infinity times 0? Because it's completely indeterminate and it's not even L'Hopital's form. Okay. What's the theme? Get it to be 0 over 0 or infinity over infinity, and you can do any one of these, right? Now, okay, so here's the thing. So in problem A, what did we move in problem A? Wasn't it x to the 10th? Because we said don't move logs, right? So let me make a little space over here. In problem A, we moved x to the 10th. Would you say that x to the 10th is algebraic? All right. Anybody remember the late method with integration by parts? Remember uv minus integral of v du? And the late method tells you like the higher one is u and the lower one's dv? Okay, well this one I made up all myself, not late. Late and then the other version Lyot that they use in college, that one's pretty much universal in America. Everybody talks about that. This one I made up using kind of those same ideas, but I decided to try to spell a different word. I was like, I hope this spells a word, you know, like late. What did we move in question B? Wasn't it the cosecant that moved, right? So the cosecant moved, and let's say that that's trig, although we did have a caveat there, didn't we? We said trig that's not sine and cosine, like the other trig functions, right? So I'm trying to think here. Well, in this case, we've got a tangent, which is one of the trig functions we said we were supposed to move. We have 2x to the first minus pi, which is kind of like x to the 10th. It's algebraic. We've moved both of those types of functions so far while we left the other one all by itself, basically, right? So who moves? Who gets priority? How does this little word spell out that's not going to be late but something else Mr. Wade made up? Well, it turns out, remember when I just said always move tangent? That's right. Tangent and cosecant and secant and cotangent, they all take priority over anything that you would consider to be algebraic. All right? So it turns out this is kind of step number 1 right here. I'll circle that whole thing. That is top priority to move. So if that's first priority according to Mr. Wade's gems, we better move tangent down and not 2x minus pi down. So now, let's do a second column. By the way, go over to a second column. And I want you to try this. Limit as x approaches pi over 2 from the right-hand side. Okay, we said tangent is going to move. When tangent moves to the bottom, it becomes 1 over tangent. But we have a name for that. It's called cotangent. And the 3 is just going to sit there, right? Like it's actually going to go down and just sit next to the 3. So tangent becomes cotangent on the bottom. Just a little bit of pre-calculus, not too much, a little bit of trig, right? No hard trig here. And then 2x minus pi, I'm just going to drop the parentheses because if it's all by itself, you don't need parentheses, right? Here's our rewrite according to Mr. Wade's rules, and then I'll give you a little acronym here in a second, okay? Now, plug in pi over 2. When you put in pi over 2 on the top, the plus sign you don't even need to because it's just a simple plug-in. Pi over 2, the 2's cancel. It's still the same thing we said earlier. It's still pi minus pi. It's 0. Boy, if we have 0 over 0, we are in L'Hopital business. All right? I guess that would be fraudulent business, right? Pi over 2. Now, this time you do have to respect the plus side. It's not a simple plug-in. It's a, do you know what the cotangent graph is doing? I went ahead and left a little piece of the cotangent graph over here, even though I erased a bunch of stuff. As you approach pi over 2 from the right-hand side, oh, wait a minute. It turns out to actually be a plug-in because pi over 2 exists. It's continuous on the cosine graph. At the asymptotes, you would have had to respect the plus and the minus. Not this time. So it turns out, sometimes, you get lucky, cotangent of pi over 2 is 0. That's why you would want to know your cotangent graph, by the way. And 0 times 3 is 0. That is L'Hopital's form. All right, let's try it. Limit as x approaches pi over 2 from the plus side of the derivative of 2x minus pi is 2. I believe we've escaped the indeterminate form. That's not 0. That's not infinity. There's no way this is going to be indeterminate. We have arrived. 3 cotangent of x. Have we ever done the derivative of cotangent of x? Nope, we sure haven't. So I'm going to teach you one of the last derivatives I'll ever show you this year. One of the few we haven't done, actually. You can add this to your list of derivatives you can now do. It'll be in your 10 things I learned about calculus in chapter 10, of course. The 3 carries because all coefficients carry 4 derivatives. The derivative of the cotangent of x is simply cosecant squared. But it changes signs. And I do believe that's the last derivative we will ever do that's new this year. And it just didn't come into play until now. Couldn't you just take this, if you're so afraid of cosecant, couldn't you just move it up to the top or side and call it sine squared? Because it's a reciprocal. It's like a reciprocal, right? I mean, I'm a math guy. I'm a self-admitted math nerd. And even I don't love to take the cosecant of pi over 2. I'd rather just do the sine of pi over 2. I mean, that's kind of the art of being a mathematician. Taking difficult math and just trying to make it easier at every turn. Okay? That's what we do. That's what you should do as a great calculus student. Try to always make things easier. All right? Don't make them harder on yourself. And of course, part of the process is figuring out, well, how do I make it easier? I'm teaching you all the ways to do that. So the 2 over 3, that's your coefficient. Leave the 2 over 3 alone. Cosecant squared on the bottom, kind of awkward. On the top or side, it would be the reciprocal sine squared. Much easier. Now just plug in pi over 2. By the way, since sine exists at pi over 2, the plus sign isn't really necessary. You don't have to worry about from the right side. It's a simple plug-in. It's kind of one of our themes today. Negative 2/3 sine squared of pi over 2. The plus doesn't really matter. And do you remember from pre-calculus that sine squared of pi over 2? You know what? We even did this in integrated 3. We actually did this in that class. It's the same thing as take the sine of pi over 2 first and then square your outcome. Remember that squared is a quantity squared, right? So you take the sine, you square it all, you put a 2/3 on it. So easy. The sine of pi over 2, which is continuous, is a peak on the sine graph. It's 1. 1 squared is still 1. Negative 2/3. Final answer. Final answer, negative 2/3, and you have done a higher level limit. Not bad, huh? It's another gem from Mr. Wade, not found anywhere. I just completely made this one up on my own. But after lots of experimentation with these types of limits, this is what to move to get L'Hopital's form. Now, when you all graduate and walk across that stage, you'll be wearing a cap and gown, and you'll move your what? Your TASL. Kind of ironic, you spend all those years in high school and even college trying to learn to read, write, do math, and we read from left to right, but then when you move your TASL, you move it right to left. After all that education, right? So what do you move? You move your TASL. Well, okay, it's kind of a modification of that. We're going to call it TASL, TASL, all right? So what's first? First priority? Move the trig functions or you're going to cause yourself a lot of work, except for what did we say? Trig except for sine and cosine, right? So let's say not sine x, cosine x, but just trig in general. The second step was algebraic stuff, all right? Anything that's algebraic. X to the first, x to the second, x to the third, 3x, 3. What else? What about square root of x, right? What about any kind of powers, x to the 2/3, okay? Third step, that's where you move the sine x, cosine of x. And then the last step, put off those logs unless you absolutely must move them, all right? TASL. And there you go, a Mr. Wade special. If anybody's wondering, by the way, if any bright students out there are like, what about the exponentials? Like, remember the late method for the integration by parts? Okay, exponentials are extremely rare in these problems, like very, very, very rare, okay? Usually, I've found that they kind of end up in the middle somewhere. Too bad it didn't quite spell like TASEL. It's more like TAE, TASL, you know? Great. But the very, very rare exponentials kind of end up right there in the middle, okay? But again, like if you have e to the x or 2 to the x, like that doesn't do all this interesting stuff like 0 times infinity, 0 times a negative infinity, 0 over 0. You just don't get that from exponentials, okay? So you rarely see those. So if you kind of go with this TASL, you're going to handle any of these crazy limits they throw at you, all right? And on that note, let's do one last problem. So in letter D, this is a unique one. In tutoring all these college calculus students, I didn't see it at any university except for Vanderbilt. And so, of course, if you go to a top-level university, This is one they like to throw out there at you, okay? This is an interesting one. Limit as x approaches infinity of this square root minus another square root. What in the world? Well, how do we start limits? Don't we try by just plugging in the number first and seeing what happens, right? Okay? So if you plug in infinity, and especially like our 3 gems of infinity, you always just plug the infinity in first and see if it helps. If it doesn't, you got to think of other means. So when you plug in infinity, you get the square root of infinity minus 1, which is the square root of infinity, minus, and then you plug infinity in over here, and you get the square root of infinity minus 2, which is still infinity. Oh, big deal, you took away 2 from infinity, oh no. The square root of infinity knocks it down to infinity, doesn't really knock it down at all. The square root of the other infinity knocks it down to infinity. Uh-oh, infinity minus infinity is indeterminate form number 3. We don't know what infinity minus infinity is because it could be 6.8. So it's indeterminate. Here's what's even worse. This isn't a fraction. All the stuff we did today was multiplication, so we made it into division, and we made it into 0 over 0 or infinity over infinity, right? We forced it to be L'Hopital's rule. That's subtraction. There's no way you're going to get subtraction to turn into division. Like, it's literally impossible. So you cannot get it to be one of these two. Therefore, this is not a L'Hopital's rule. So this is an indeterminate form that cannot go to L'Hopital's rule. What do? Confession time. The first time I was helping a student at Vanderbilt with this very problem, I was stumped for about 60 seconds, which is a long time for Mr. Wade to be stumped in math because I've had a lot of practice, right? That's what I'm saying, okay? I'm no smarter than any of you. It's just I've had the practice. And I was sitting there stumped, and then you know what I do when I get stumped? I start listening to my own advice. I start listening to my own words that I give all of you, and it helps me too. So I started thinking to myself, okay, can't make it division, can't make it 0 over 0, can't make it infinity over infinity. Bing, 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 bing. Every time you have a square root plus or minus a second term, which doesn't necessarily have to be a square root, but if you have 2 groups, addition or subtraction, and at least one of them is a square root, it is always the conjugate, no matter what. And I realized it's just an old conjugate problem. This is all technically over 1. The conjugate of the numerator would be first term, square root of x minus 1, change the sign into plus, second term stays the same, square root of x minus 2. That is the conjugate, and if you do it to the top, you do it to the bottom. And the student that I was tutoring was also extremely bright, and the professor had not taught them in class how to do this. They just threw it at them like they do in college. And this really, really bright kid I was tutoring, she couldn't figure it out either. And then when I said, I think it's a conjugate, and we started to do it, she goes, oh, that's brilliant. It works. And she never forgot it. And I never forgot it either. And now you won't forget it, right? So it's just kind of the joys of figuring out some of this stuff on your own, you know? I mean, this is not one that I ever do until I saw it. And so I want you to see it. So remember the rules of conjugates. The one that is the conjugate, you want to FOIL the whole thing out. The one that's not the conjugate, you never do anything with it. So on the top, FOIL the conjugate, don't FOIL the other. The square root times itself just gives you the inside, just a normal, regular x minus 1 quantity. The outer inner always cancel each other out in a conjugate. And then when you do the last, it'll be a minus times a plus as a minus. And a square root times itself is the inside or radicand, is what we call the inside of a radical. And then on the bottom, you just leave it 1 times whatever. We'll just drop the 1, basically, right? Okay, use your conjugates, all right? Now, try to plug in infinity. Wait, you're still going to get infinity over infinity until you realize that the subtraction sign distributes into the second group, and you have x minus x. It cancels out the x's. Beautiful. Okay, because we don't want infinity over infinity. Although, because you do get infinity over infinity, actually, you would get infinity minus infinity on top, so you would actually get indeterminate over infinity. So actually, you wouldn't even have a L'Hopital's form. But once you cancel out the x's, you get the limit as x approaches infinity of the x's cancel. Negative 1 minus minus 2 makes negative 1 plus 2. 1 over. And as soon as we saw that 1, you know what? We knew we were in the clear. Okay? I hope you love this stuff as much as I do. I hope you realize that this is a confession, that Mr. Wade's human. I'm just as human as you are, and I can get stumped on some of these that I haven't written myself, but I can follow my own advice, and you can follow my advice. And when you learn from somebody who's been through the ringer for years and years and decades, you can also be that person that eventually teaches people how to do this. Now plug infinity in, and you get the square root of infinity minus 1 is infinity. You get the 1 on top, right? Plus square root of infinity minus 2 is infinity. Now, infinity minus infinity is indeterminate. But it turns out with the conjugate to become infinity plus infinity, which you can absolutely do. Infinity plus infinity is infinity. And you get 1 over infinity, remember? One test question right out of infinite test questions, you pretty much just got a 0. 1 over infinity is 0. We have solved this limit. So infinity minus infinity can actually be 0 sometimes, but not always, right? It can be anything, okay? Indeterminate. Love that problem. So there you go. If you ever get stuck, guess what? So does Mr. Wade. Think about what I've told you. Try to use your knowledge and try to get out of it. So don't forget that. Don't forget conjugates from chapter 8. We already did those in chapter 8. And don't forget TASL, T-A-S-L, and you can now become a limit genius. Until I throw the ones at you in 10-3 that you can no longer do with this method. So I'm going to have to show you another method, but don't worry, it's going to be fun. Okay, do your homework. I'll see you next time.
Hold it now.
But once you've gotten to this, just hold on. All right, how about this for a new trick? Wait, that's not going to work. So today we actually, or you can move the cosecant to the bottom. And on that note, we debut. Never move the natural logs. Didn't we move the tangent, right? No, we sure didn't. It's the backwards from keep, change, flip, right? It's kind of what? Flip, change, and keep, right? Flip, it's flip, change, keep. That's our new FC. I'm not going to use that acronym because that's not going to lead us down a very good path.